Good morning. In today's class, I am going to tell you two applications of tangent law in electrostatics. See here, from Coulomb's law, force of attraction or repulsion, from Coulomb's law, or Coulomb's law says force of attraction or repulsion between any two charges in air or free space is given by 1 by 4 pi epsilon naught q1 q2 by r square. Coulomb's law, from Coulomb's law, force of attraction or repulsion between two charges q1 q2 separated by a distance r is given by 1 by 4 pi epsilon naught q1 q2 by r square. Now, in any medium of dielectric constant k, force of attraction or repulsion is given by 1 by k 4 pi epsilon naught q1 q2 by r square. Okay, that is force of attraction or repulsion between two charges in any medium of dielectric constant. Now, let us go back to tangent law which we studied in our vectors. See here, a simple pendulum is suspended and it is pulled aside through an angle theta by a horizontal force F, and we proved that from tangent law F is equal to mg tan theta. So, this we know pretty much well from the concept of vectors. So, when a simple pendulum of bob mass m is pulled aside through an angle theta by a horizontal force F, then we proved that F is equal to mg tan theta. Now, here coming to electrostatics, two simple pendulums, two identical simple pendulums, meaning lengths are equal and masses of the two bobs of the simple pendulums are equal. They are suspended from the same point. So, here if two simple pendulums are suspended from the same point, they will be like this, isn't it? The two simple pendulums, they will be like that. Now, if they are given charges, then because of the repulsion, they will be separated like this. So, here this is the situation we are going to study now. So, two simple pendulums of equal lengths and equal masses are suspended from the same point. The bobs of the pendulums are given equal charges plus q each. Then, because of the repulsion, the arrangement moves apart as shown. So, here so that each string is making an angle theta with the equilibrium position. So, here force acting on this bob and on this bob, they are equal and opposite from Coulomb's law. If the separation between the two charges is r, then from Coulomb's law, force of repulsion between those two charges is 1 by 4 pi epsilon naught q1 q2, that is q into q square by r square. That is from Coulomb's law, force of repulsion between the two charged bobs of the pendulums. Now, from tangent law, if you imagine this as the first pendulum, it is being pulled aside through an angle theta. So, this F provides the horizontal force to pull that pendulum aside through an angle theta. So, 1 by 4 pi epsilon naught q square by r square is equal to mg tan theta. This is the most important equation here. I think you followed that. So, I am explaining you the situation. Two identical simple pendulums with charged bobs plus q each are suspended from the same point. because of like charges, as like charges repel each other, the two pendulums repel each other till they come to an equilibrium position. At that equilibrium position, force acting on each of them is 1 by 4 pi epsilon naught q square by r square. But when a simple in order to pull the simple pendulum aside through an angle theta, the necessary horizontal force is F is equal to mg tan theta. So, here that force is provided by the Coulomb's force here. So, 1 by 4 pi epsilon naught q square by r square is equal to mg tan theta. Here we talk about a special condition. Follow that carefully. Here the arrangement is immersed in a liquid. The arrangement is submerged or immersed in a liquid. In a liquid of dielectric constant K, density rho. Let D be the density of the bob. I am telling you once again, that entire arrangement is completely immersed in a liquid of dielectric constant K, density rho. Let the density of each bob is equal to D. Here the condition given is theta remained constant. Theta remains constant, that is the condition given. Okay, so the arrangement is immersed in a liquid of dielectric constant K, density rho. If theta remains constant, what happens? Let us see. Here 1 by, in a liquid of dielectric constant K, force becomes 1 by K 4 pi epsilon naught q square by r square, m g into 1 minus rho by d. When the object is immersed in a liquid of density rho, then from Archimedes principle, g dash is equal to g into 1 minus rho by d, mg tan theta. But here actually you have to take tan theta dash, but I gave you theta remains constant. So, from this expression you see what do we get here. So, this is equation 1, this is equation 2. See here, if you just divide like this, 1 by 2 implies 1 by 4 pi epsilon naught q square by r square, they get cancelled, k goes to the numerator. So, k is equal to mg tan theta by mg tan theta gets cancelled, k is equal to 1 by 1 minus rho by d. Very important formula which we will be using while solving the problems in objective examination. I am repeating the concept. So, go through the problem step by step. Here from the same point, two identical simple pendulums with are suspended, with charged bobs are suspended. They are drawn apart because of electrostatic force of repulsion through an angle theta. Each pendulum moves through an angle theta and then rests in equilibrium position. Then from tangent law, F is equal to mg tan theta. So, the force on each, horizontal force on each bob is created by electrostatic force of repulsion between the charged bobs. If the arrangement is in air or free space, 1 by 4 pi epsilon naught q square by r square is equal to mg tan theta. If the entire arrangement is immersed in a liquid of dielectric constant K, from this expression 1 by k 4 pi epsilon naught q square by r square is mg into 1 minus rho by d into tan theta, because in here I mentioned the condition even after submerging that in a liquid, the angular separation remained constant. So, from this k is equal to 1 by 1 minus rho by d, that is one method used for the determination of dielectric constant of a liquid. Okay. And now based on this, there is another question. Look here. So, two identical simple pendulums with charged bobs are suspended from the same point. Then each moves through an angle, if they are identical, each of them moves through the same angle theta. Right? Now here 1 by 4 pi epsilon naught q square by r square, r is the separation between them, q square by r square is equal to mg tan theta. Right? Now here, if the arrangement is taken into a satellite, so that will be equal to 0. Or if the arrangement is placed in a freely falling lift, into a satellite or to a freely falling lift. Even in case of freely falling lift, apparent acceleration becomes equal to 0, not the real acceleration. Apparent acceleration due to gravity becomes equal to 0. Then what happens to that? 1 by 4 pi epsilon naught q square by r square is m, apparent acceleration becomes 0 into tan theta. From this tan theta is something by 0, infinity, theta is 90 degrees, meaning the string makes an angle 90 degrees with the vertical. This makes an angle 90 degrees with the vertical. Then the angle between the two strings becomes 180 degrees. So, when two identical simple pendulums are suspended from the same point, if that arrangement is taken to a satellite or in a freely falling lift where acceleration due to gravity apparently becomes equal to 0, then the angle between the two strings will be 180 degrees. Here, instead of doing all these things, if you have the common sense, you can answer, isn't it? Suppose if the two strings are like this, there is only electrostatic force of repulsion, there is no restoring force due to gravitation, because gravitational force apparently becoming 0 there. So, simply the force, only because of force of repulsion, the two strings just become straight. Okay? So, when the arrangement is taken to a satellite, angle between the two strings becomes 180 degrees. Now, another model I am telling you. Look here, this is a simple pendulum with a charged bob of charge q. It is oscillating in a uniform electric field of intensity E. So, then here not oscillating, it is placed in a uniform horizontal electric field of intensity E. Then here it will be pulled through an angle theta by the force due to this electric field. So, here F is equal to QE, and that QE provides the necessary horizontal force to pull it aside through an angle theta. So, in this problem QE is equal to mg tan theta. So, I am repeating the problem again. A simple pendulum with a charged bob is placed in a uniform electric field acting along the horizontal direction. Then the bob is experiencing a force in the field direction. As a result, the pendulum is pulled aside through an angle theta. From tangent line, F is equal to mg tan theta. F here is nothing but QE. So, QE is equal to mg tan theta. Is it okay? And I am telling you another expression. Look here, what is the expression for force on a charge q in a uniform field of intensity E? F is equal to QE. Suppose the problem is given like this. A charge is kept stationary in air by an electric field. A charge is kept stationary in air by an electric field implies what? See here, when a charge is in air, its weight mg definitely acts in the vertically downward direction. So, it falls down with acceleration g. But it is kept stationary means this is being balanced by electrostatic force. So, what must be the direction of electric field so that force on this positive charge is upwards? Very obviously, it should also be in the upward direction because force on a positive charge is in the field direction. So, here force on the charge Q is QE in the upward direction if that QE balances the weight, then the net force acting on it becomes 0 and the charge keeps just floating, or the charge is kept floating in midair, or if the charge is kept stationary in air by applying an electric field. If the charge is positive, electric field direction is upwards. If the charge is negative, electric field direction should be downward so that force will be up. Again, in that case also QE is equal to mg. So, I will stop here. Thank you and bye-bye.